Okay, hi guys. This is like my seventh time trying this. I found this program and I'm gonna just try it out. I'm not sure. I'm very tired, and the last time I tried this, I went for 30 minutes talking just to find out I had not started the recording yet, and so I am very pissed at myself. So hopefully this is the last time. If it isn't, I'm probably just gonna do it some other day because this is ridiculous. Okay, so this, like I said, these videos, by the way, this is the seventh time, and it still feels very awkward talking to myself. Like, I know I'm going to be sharing this video with you guys, but I'm talking to a computer screen. It's kind of strange. So, yeah, like I said before, these videos are for anyone that misses the actual classes that we do online, and you can, or if you just want to review, then you could watch these videos or whatever and catch up or something. Okay, for anyone that didn't make it on Friday, we covered some stuff. We covered the, I'm still getting used to this tablet that TJ lent me, by the way. So we cover the quotient rule and the chain rules of derivatives, and we also talked about the graph of f prime, or you also might see it written like that. Yeah, very messy. I know. Okay, so I'm not gonna prove any of these rules to you because it will take forever, especially using this tablet. So I'm just gonna go over what they are, do some examples, and hopefully you understand how to apply it. Okay, first is the quotient rule. It's gonna be the quotient rule. What the quotient rule says, or when we use it, is when we have a function divided by another function. This is when, and we're trying to find the derivative of this. So we're trying to find the derivative of this. Then the derivative is equal to, wait, okay, I'm not sure. I'm not gonna cover the product rule. I'm pretty sure some of you missed it. Maybe if you guys missed that day we talked about the product rule, you can come talk to me or something. I'm just gonna go straight off the quotient rule right now. Okay, so the quotient rule says that if you have two functions, one divided by another, then I'm gonna give you the definition first, and I'll show you an example what this means right here. So what you do is you take the derivative, or no, you write the bottom function first, so just the g of x. You write g of x times, can't make a dot with this tablet, okay, times f prime of x, or in other words the derivative of f, minus just the function f of x, so just the top, just this top function right here, times g prime of x, which is the derivative of g, or the derivative of the bottom function, all divided by g of x, so just the regular g of x, but squared. This is definition of the quotient rule, or definition of the quotient rule. And the proof is relatively easy-ish. It's just using the product rule, and then you can prove it from there. The product rule proof is long, but we did that before. So if you just, I'm not gonna explain the proof right now. Okay, so just ignore that. So this is the quotient rule, and what it means, or when you use it, is a function divided by another function, right? An example of this is like sine of x all divided by cosine of x. This is one function, this is f, and this is g, right? So function divided by another function. So they're relatively easy to spot, like x squared divided by natural log of x. This is also a time, if you're trying to take the derivative of this function right here, you use the quotient rule, because this is two functions divided by each other, right? So this is when you use it. Now actually, how about actually using it, right? So let's do sine of x over cosine of x, and we're trying to take the derivative. This notation here is this notation means that you want to take the derivative of sine of x divided by cosine of x with respect to x. And what respect to x means, it means that the x is the change in a way. It's the one. It's okay. In simple terms, I guess you can just say that the x is the one you focus on. It'll make more sense when we talk about implicit differentiation, which we haven't covered at all, and I don't think I'll cover in this video, but it'll make sense later. So let's focus on the derivative of this using the quotient rule. So the quotient rule tells us you take the bottom function and you just write it out. So this is simply cosine of x times the derivative. Do I need to write it out again? This is. Yeah, that's not what I want. That's not what I. Okay, I'm just. Yeah, no. Okay, that didn't work at all. So I'm not gonna. Yeah, I should write it out. Maybe I'll edit this out later. How to do this? Just my mouse. Yeah, I see that's what. Good enough. Okay. Alright, I might just edit that out later. So the quotient rule tells us that if you have, remember, a function divided by another function, then its derivative is g of x, just the bottom function, times the the derivative of the top function minus just the top function written out times the derivative of the bottom function, all divided by the bottom function squared. Alright, so just using this, like it'll become like a second sense to you after using this like a million times. You don't write this out every time and like base it on, but this is just to show you exactly what we're doing. So like it says, bottom function, just write it out. G of x right here is cosine of x, we just write it out. That's the cosine of x. Times f prime of x. F being the top function. Top function is f, bottom function is g. So f prime of x is the derivative of the top function. The derivative of sine of x is cosine of x. This was in the list I gave you. Some of you might have missed that, and I might later write a list of derivatives you guys have to remember, and if we have time sometime, I might prove them to you, because they're not that hard to prove, but some require knowledge of trig identities and whatnot, and you guys may not know or whatever, but they're not usually that hard to prove. Anyways, so minus the top function written out, f of x. Our f of x here is sine of x, because you realize that this is f of x, and then this is g of x. Hopefully you kind of figure that out. So minus sine of x. Also, I'm not sure how the video quality is. This might be really laggy to you guys, or it might run smooth. I try to lower the settings down as much as I could without affecting the video too much. It's recording right now in the background. I'm not, hopefully, not just that I totally forgot to turn on again and talk for 30 minutes. Sorry. And then derivative of g of x, which is the bottom function. Derivative of cosine of x. Also, I gave it to you guys. It's negative sine of x. All divided by the bottom function squared. Our bottom function here is cosine of x. Cosine of x, and we square it. Square. And remember, you won't see it in this fashion. Usually it's going to be written cosine squared of x. That means the same thing, just that this is much clearer because we don't need to write the parentheses, making it really ugly looking. So yeah, this is just cosine of x and the whole thing squared. But we write the square in front of the cosine, or in front of the, after the cosine, but in front of the angle. So this here is the derivative. That's it. If you're really lazy, or if you're totally fine with losing points on your test or whatever, just write like this and you'll be good. But obviously Mr. Woods or your future calc teacher will tell you to simplify it. So we will cosine of x times cosine of x, that's cosine of x squared. And remember, we don't write like this. You have to get used to writing cosine squared of x. And then minus sine of x times negative sine of x. There's a negative here, and there's a negative here. This is multiplication. The negatives cancel out. Plus sine, and for the same reason, we don't write sine of x and then parentheses squared. We just write the square out front and put the x right there, or put the angle, whatever the angle is. All divided by cosine squared of x. And this is still derivative of sine of x, cosine of x. I'm getting sort of used to this tablet. It's not as ugly as when I first used it, but it's still pretty bad. So this might be as far as you can get, because, and I don't blame you, because we didn't learn any trig identities. Trig identities, they're identities that involve cosine and sine and whatnot. That you usually learn in trigonometry. And we really didn't do any of that. So last year I spent maybe 2 weeks just memorizing trig identities that I sort of proved to myself. Some I didn't bother because I had to focus on calculus. So if you ever have time, or you just like, I love math, I just want to just learn trig identities. Yeah, that it helps. Actually, there are some trig identities you will have to learn. I'll tell you which ones. They're very useful for integration later on. But yeah, it's fine right now. So this is not a trig identity, obviously, from getting from there to here. All I did was break up the fraction. Since this cosine of x, cosine squared of x is the denominator, I just broke out the function into the two pieces. If you add them together, you get the top part again. But this is where you apply the trig identity. The trig identity here is that. Oh, actually, before that, I'm gonna start writing. This is my last time I'm gonna write this. You just got this is still a derivative of this, right? And this is still f prime. I'm not f prime, whatever prime you want to call it, whatever function you want to call it. So this right here is obviously 1. That should be an obvious identity, not a trig identity. This right here is not you should know. We didn't. It's not much proof here. Tangent of x is equal to sine of x over cosine of x. This you guys should know. This isn't a trig identity. So if tangent of x is equal to sine of x over cosine of x, then tangent squared of x is this squared, which is what we have here. So 1 plus tangent squared of x. And actually, you should be able to get to this point, at the very least, this right here. And then I would, it's okay if you didn't know that 1 plus tangent squared of x is actually equal to this right here. is a trig identity, and it's equal to secant squared of x. So it's alright if you can't get from this portion to this portion right here, but yeah, okay, so the reason I did this problem is to show you how to use the quotient rule, as well as show you a very important derivative, one you should just memorize. That, look what we took the derivative of sine of x over cosine of x, and I'm not sure if you recognize it, but this is actually equal to, like I said right over here, tangent of x is equal to sine of x over cosine of x. So this is tangent of x. So if you take the derivative of tangent of x, you get secant squared of x. And remember what secant is? Secant is just 1 over cosine. So this is 1 over cosine squared of x. But secant squared of x, right? Yep, so derivative of tangent of x, tangent of x is not equal to secant of x. The derivative with respect to x of tangent of x is equal to secant squared of x. This, memorize it. It's very important. And I'm not cotangent of x. If someone tells you to take the derivative of cotangent of x, you'll do the same process. You'll take it apart. Right now this is a function, but you don't know the derivative of it. But you do. But if you take it apart into its cosine of x over sine of x components, now it's just a derivative of a function of that's written as a quotient of two different functions, and we know the derivative of each individual function here, and we can take the derivative. And if you go through the quotient rule, and it'd be good practice for you to do so, but I'm not going to do it. Is that if you do the same process we just did for tangent of x or sine of x over cosine of x, and you do it for cosine of x over sine of x, you'll find that you'll get negative cosecant squared of x. And this is the derivative of cotangent of x. So derivative of cotangent of x, which is the derivative of cosine of x over sine of x, is equal to negative cosecant of x. So it's not that hard to memorize. Like, it's very symmetrical in a way, which is what's so beautiful about mathematics. If you'll notice that there's a lot of symmetry going on. So if you take a derivative of this, you get secant squared of x, and then cotangent, the derivative of cotangent of x, is equal to the cosecant, or negative cosecant squared of x. It's not that hard to memorize because they're both squares, and the tangent of x goes with the secant squared of x, and then cotangent goes with the cosecant, and they're both squared, and then the co is negative. That's all you have to memorize. The co corresponds with the co over here, I guess. If that's a good way to memorize it, I don't know. But that you just have to memorize that this one's negative, and that's about it. So 2 important derivatives you should probably memorize. Very important. Alright, that's the quotient rule. Maybe I'll do one more, or actually I'm not it's fairly easy. It's not that hard. You just memorize how to use the quotient rule and you're good. Yeah, I don't think I'm gonna do another one. If you have further difficulties with the quotient rule, you can come see me at school or whatever, and I can help you further on there. So next up we have the chain rule, and this is basically where we finished off on Friday. We covered some. Oh yeah, that's right. I'm gonna talk about the graphs of f prime, but I'll do that after chain rule. So the chain rule, these are all rules for derivatives. This is your final rule for derivative. After learning this one, you'll be able to take the derivative of any function. And we did one on Friday that looks ridiculous. They can get pretty rigorous. Oh, indigestion, I guess. I'm sorry. Yeah. So they can take a little time depending on how long the derivative is, but you can. The thing about derivatives derivatives is that you can take the derivative of any continuous function. We covered times when derivatives doesn't exist. I don't I might do that. This is the problem with classes where so many people miss whatever. We talked about that like last Saturday, but I don't know if I want to cover it again. I might. Back to chain rule, yeah. So the thing about derivatives is that you can take any derivative as long as the function is continuous, and that there's no cusps or corners. So very quickly, a way you can't take a derivative if there's a cusp. That's a terrible picture. This is a cusp. So the derivative exists on this here and on this here, but will not exist at that point. There's a cusp right there. It doesn't exist in sharp corners, which is like the absolute value, and it doesn't exist right there. And it doesn't exist if there's discontinuities like this. If the function looks like this, and then it's not continuous, you can't take the derivative. That's about it. That's like 5-second calcul or something. It just yeah, so if you have trouble with that, I can talk to you later. I don't know. I don't really want to cover it. Oh, sorry. Chain rule. So the chain rule is for using in composite functions. If you remember what composite functions are, they're a function within a function. Like this. These are they're not that hard to recognize, but obviously there's it's not. You have to use a chain rule, you have to recognize when there's a function within this function. You can see sine of x squared of x. This looks like one straight function, doesn't it? But it's actually, you have to recognize that sine squared of x is a composite of two different functions. And if you write it out like sine of x squared, hopefully you can recognize that it is indeed a function within a function. The two functions here is that f is equal to, or let's do the f, let's use y. F of y is equal to y squared, and g of x, actually, no, I'm gonna use straight up x's. Okay, so f of x is equal to x squared, and g of x in this case is equal to sine of x. And this is a composition function. This is a composition function. If you put g of x within f of x, so you put g of x inside f of x, wherever you see an x in f of x, you put your sine of x, right? So if you put your sine of x inside the x squared, you get sine of x squared. And that's what we have here, and it will be shorthanded to this. So you have to recognize that this is a composition function. You'll get used to it. It's not that hard. Another one would be like, natural log of x cubed. This is a composition function that's a lot easier to see. G of x, in this case, that's g of x. That's inside f of x. F of x being natural log of x. So if you put g of x inside f of x, or you put x cubed inside natural log of x wherever there's an x, you get natural log of x cubed. And this is another case where you would use the chain rule. So yeah, that's about it. I'm going to do an example now. Okay. Alright, chain rule. So I'm going to write it out again. Chain rule, if you have a function... Oh, I didn't even write the definition yet, did I? Yeah, so if you have a function within another function, and you want to take its derivative, you'll take the derivative of this thing right here. It's then equal to f prime of g of x. I personally like the chain rule the best, because I think it's easy to do. I'm not sure. It's really easy to memorize. That's what I think. So you take f prime of g of x times g prime of x. Yeah, this might look very complicated in a way, but it's actually very simple. So what this is saying is that to take a derivative of a composition function where g of x is the interior function and f of x is the exterior function, then you take the derivative of f and you evaluate the derivative of f at g of x, and then you multiply it by just the derivative of g of x. This portion right here, you should already know what it means, just the derivative of g of x. By now, you should be able to recognize notation fairly simple. This means derivative of g of x. It could be also written as the derivative of g with respect to x. That's another way of writing this right here. So this is the part. This part should be the only part that you should not understand, if any, at all, because you should be able to recognize notation by now. Okay, so what this means is that you take. It's a lot easier if I just do an example actually. So let's do natural log of cosine of x. This is f is equal to this. Oh no. How about g? I'm trying to use the less. I don't know. I'm very tired. I can't. Oh, sorry. So let's h. Sorry, h is equal to this. H of x. H of x. That's h of x is equal to natural log of cosine of x, and we want you to find the derivative of h with respect to x. So this is the same thing as h prime of x. I'm trying to get you used to notation, but you should. It's not. This notation is not that big a deal. You should be able to recognize it. So all this is saying is to find the derivative of this piece right here. And what the chain rule tells us is that we want to take the derivative of the exterior function evaluated at the interior function. The exterior function f is equal to natural log of x. This is a composition function made up of natural log of x and cosine of x. You have to recognize that. So g is equal to cosine of x, right? So if you put g inside of f, then you get this piece right here. You put the cosine in the x right here, you get natural log of cosine of x. So since this is a composition function, we use the chain rule. This is a composition function, we use the chain rule. So take the derivative of the outside function and then evaluate it within the interior function. What that means is that oh wait, that's exactly what it means. But so what's the derivative of natural log of x? That's one of the ones I gave to you. That's 1 over x. So this would be f prime. That's f prime, right? That's f prime of x though. We don't want f prime of x. We want f prime evaluated at g of x. That's what our chain rule tells us. Oh, we want this. That's what our chain rule wants, right? So we don't want f prime evaluate x. We want to evaluate g of x. So we just evaluate g of x. What is g of x? G of x is cosine of x. So instead of x, we put the x. We put g of x there. And what g of x is the interior function. So let's just put cosine of x. And that's it. And then you multiply it by the derivative of the interior function, and that's just cosine of x. Derivative of cosine of x is negative sine of x. Oh, this is strange. Okay, that's I'm not sure. So if you simplify this would be negative sine of x over cosine of x. I guess that would equal negative tangent of x. Okay, okay, that was totally unintentional. So I guess the derivative with respect to x of natural log of cosine of x is equal to negative tangent of x. Yeah, I mean, it makes sense, yeah, obviously, but I learned something today. This is obviously not something you have to memorize. You don't have to memorize. Natural log of cosine of x is equal to negative tangent of x. But okay, that's pretty cool. Yeah, see, this is why math is so awesome, because sometimes you discover things on your own. Okay, so that's a very simple application or use of the chain rule. It's called a chain rule because you can link it as a chain. for example, you can take as many as long as there's a composition function. You can keep chaining them onto each other. You can so let's say you have x of g of z of x. This is one huge composition function. So chain rule tells us that if you can take the derivative of this. The derivative of this would equal x prime evaluated in the interior function, which is this piece of crap right here. Is that in parentheses? Did I get it right? There's one more. Times g prime evaluated at its interior function, z of x, times, and finally z prime of x. And this is why it's called a chain rule. It can even get longer. You can put more functions as long as they're composition functions of each other, and you just keep taking the outside function, the derivative, evaluate at the interior function, and then go on to the next layer, and take the derivative and evaluate at its interior function, and then keep going all the way until you get into the very middle. So yeah, like I said to the Friday class, I tend to think of this as like peeling an onion. And not because it makes you cry. Well, I guess it could if you see something like 10 layers deep. But yeah, so it's like peeling an onion because you peel one layer and then you keep going after each layer until you reach the end. And some layers might be long. Some onions might be long, have more layers than others. So let's do example. I'm gonna do some really easy example. E to the cosine to natural log of x cubed. Let's take the derivative of this thing right here. This is some ridiculous looking function, right? I mean, you could graph this. I don't know how it would possibly even look like, but the great thing about derivatives is that you can take the derivative of any function as long as it's continuous. And since these are all continuous functions, and they're yeah, this is a continuous function. So, alright, first layer. So the first layer is the very outside function. The very outside function is e to the x. This is the very outside function. And we want to take its derivative. Derivative of e to the x, I gave it to you guys. Just off to the side here. Derivative with respect to x of e to the x is equal to e to the x. This is why this is my favorite function. Every time I see it, I'm like, yes, no work to do. And it keeps reappearing. It's a very, very important function. Not just because it's easy, but it's used a lot. So yeah, the derivative of e to the x is e to the x. So we take the derivative of the outside function, and that's this. But we want to evaluate it within its interior function. So this right here. So what we end up doing? Let's just use eraser. So what we end up doing is just rewriting this the function. So we took the derivative, which is the same function, and we just evaluate within its interior function, which is this right here, and we just end up with this same thing. But we're not done. Now we gotta take the so now we have to take the next layer. Okay, sorry. Let's take the derivative of the next layer and evaluate it at its interior function. The next layer, the thing about chain rule is that you have to realize what layer comes after the next. So the next layer is cosine of x. This is your next layer. We're not multiplying cosine of x. I'm just saying the next layer is cosine of x. It's this portion right here. And the very outside thing is cosine, right? So we take the derivative of cosine of x. What is that? That's negative sine of x. That's the derivative of cosine of x, but we don't want this. We want to evaluate it at its interior function. Its interior function is this, because this is the function inside cosine of x, right? So at this x right here, we evaluate the interior function, this interior function right here. Not this derivative, not like that, just written out, right? While parentheses going on. Yeah. And then we move on to the next layer. The next layer is natural log of x. This is your next layer. Or I already drew right there. Yeah, this is your next layer. And the derivative of natural log of x is 1 over x. So we don't multiply by 1 over x, but 1 over x evaluated at its interior function, that's x cubed. So instead of x, it's x cubed times the next and final layer, this layer right here, x cubed. The derivative of x cubed, the power rule tells us is 3x squared. And this is the derivative. This is the derivative of this complicated looking function, and we end up with the even more complicated, ridiculous looking function. So if they tell you to evaluate, if they tell you to find the slope at a given point or x value for this function, let's say they want you to find the slope at the point, or I don't know, if you plug in 1 and then whatever you get for 1, when you plug in 1 here and then evaluate all this, so that's some number. They want you to find the slope at that point for this function. Then you just have to, or not just have to, it's a very complicated long function here. So you plug in 1 for every x here, and whatever you get, let's say that equals 30. I said 30, I don't know why I drew that. 36. Then the slope at this point is 36. Right? That's what f prime always tells us. F prime always tells us the slope at every x value, right? As long as it's continuous. Okay, so that is the chain rule with 3 layers. So one final example is a combination of all that we have done. Okay, just checking am I recording? Okay, I'm recording. I just talked on for about like 40 minutes and I didn't check once, or I didn't check at all, and that would have been smart. So let's take the derivative with respect to x of natural log of x times. Okay, I'm not gonna make it too complicated. I just remember the last time I did this. It took forever already. So natural log of cosine of sine of x. Actually, of 3 of x. Yeah. Actually, this might take a while. I'm not sure. And all this is divided by x to the 3x to the x squared. So derivative of this looks ridiculous. It's not that hard. It might take a while work-wise, but it's not that hard. You just don't lose your place when you're doing these things. So if you're taking the derivative of this, you have to realize that this is just 2 functions. This top ridiculous looking function divided by 3x squared. So what we do is, the moment you see any division going on like this, you know, and you take a derivative, you know you're going to probably use the quotient rule. So the quotient rule tells us we want to write just the top function, or sorry, the bottom function, just write it out. So remember, our quotient rule says just write out the bottom function, 3x squared, times the derivative, and here we go. Okay, so times the derivative of the top function. This is, this is the fun part. This is the part you've been waiting for. The derivative of the top function. This is all chain rule. I could have added a product rule in there and just make you suffer, or make myself suffer. What am I talking about? Yeah, so I wasn't gonna do that. That would have took even longer. But everything is possible when taking derivatives. So, or all functions can be. Yeah, I've already proved myself like 30 different times. So we just. I'm going on a side here because our quotient rule tells us to write out the bottom function and take the derivative of the top function, multiply them together, right? Bottom function times f prime of x, and this top part right here is f of x. So we need f prime. We need a derivative of this right here. So I'm going to do an aside to find f prime. This is not find the derivative of this entire thing. This is just find the derivative of the top portion. So we need to find the derivative of f prime of x. Oh, let me write f of x again. F is equal to, what is that? Natural log cosine sine 3. Natural log of cosine of sine of 3x. See, my philosophy has always been do the most complicated problems, so you never have to focus on doing 100 easy problems, because understanding how to do the at least one or two complicated function or problems, then you should have no problem with easier. You shouldn't have to waste time doing easy problems, right? So this is f. We need f prime. You won't see something like this on the AP exam because this will take a while. They don't make you guys do that. So f prime is the derivative of the most. This is all just composition functions, right? This isn't any product rule, quotient rule, or power rule going on here. Well, this right here might be. This is sort of power rule, I guess. But yeah, so this is just all chain rule. So chain rule tells us derivative of the most outer function, which is natural log of x. Derivative of that is 1 over x. But we want, instead of 1 over x, we evaluate its interior function at the x. So 1 over not x, but cosine of sine of 3 of x times the next layer. So we finished the first layer of that's natural log of x. We move on to the next layer, which is this cosine of x, of cosine of this thing right here. That's our next layer. The derivative of cosine of x is negative sine of x times negative sine, not negative sine of x, but its interior function, right? Interior function being sine of 3x. I might run out of room. Times the next layer. I'm going to just expand this really quickly. Alright, great. And I just heard my computer bump up like 5,000 RAM or something. My computer's going to crash for no reason. It's literally the crappiest computer you can possibly buy with money. So I lost my. Oh, okay, yeah. So we just took the derivative of cosine of x, which is negative sine of x, and then evaluate it within its interior function, sine of 3x, right? We just plugged it in right there. Now we have to move on to the next layer, this sine of x layer. Derivative of sine of x is cosine of x. Cosine of x, but not cosine of x, but it's evaluated within its interior function, which is 3x. Times, and the very last part, times the derivative of the interior function 3x, which is just 3. And it's, well, if it's every time you see a constant in front of x, the derivative of this is just going to be the constant, because if you apply the power rule, that's x to the first power, you take out the 1 to the front, then 1 minus 1 is 0, so x 1 to the x 0 power, which is just equals to 1. If you have a 3 here, then this is a 3, this is a 3. So that's all I did. Oh, okay. So yeah, this is f prime. What we have here is f prime. I might or might not. Okay, I'm gonna just write. All I'm doing right now is I'm just gonna write, make it more neat. You should. I'm not gonna explain what I'm doing. I'm just gonna put them together. That's all I'm doing. So this is negative sine of 3x cosine Can't you not change the size of an eraser? What the heck? So cosine of 3x. Oh, I should put the 3 out front here. Yeah, so all I'm doing is I put this piece with this piece, and then the 3 is going to go all the way on the front. And remember, this is a negative. All divided by cosine of sine of 3x. Sine sine of 3x. This is f prime. I just made it look a little neater. And now we have f prime. So yeah, I'm not gonna rewrite this right here. Did I get the end? Okay, good. Copy. Actually, just copy. So yeah, this is all just to find the derivative of the top function. So now we're back to using the quotient rule. We haven't even finished this yet, but the hard part's gone. So we had to find f prime because the quotient rule tells us to write the bottom function, which is 3x squared, times the derivative of the top function. The top function being this thing. And we finally have the derivative of the top function. The derivative of the top function is what we just did. Paste, no, where is it? This is the derivative of the top function. Yeah, this is all just for quotient rule. Ridiculous, right? Oh gosh, I'm running out of room. Minimize it a little bit. So I'm getting rid of all this. Great. So this right here. This is the bottom function times the derivative of the top function. This right here, right? I'm gonna move this down. Oh god, hold on. What do I do? Alright. Keep in mind, this is the derivative of this entire piece now. We're working with the entire piece again. So, bottom function times the derivative of the top function. Bottom function times the derivative of the top function minus, this is just quotient rule, the top function, just written out, no derivatives, none fancy or anything. So just the top function times the derivative of the bottom function, and that's easy. This is the quotient power rule, which is just take out the 2, take the 2 out front, so 3x squared, you take the 2 out front, and then decrement this power by 1, so the 2, so it's going to be 2 times 3x to the first power, or 6, which is equal to 6x. So the top function times the derivative of the bottom function, just 6x. And now all this is divided by the bottom function squared. So 3x squared squared, or which is also equal to, you take the, so it's 3 squared x to the 4th, right? And that's just going to be 9x to the 4th. Oh, so bottom function squared, the 3 times the so this, if this entire thing is squared, then you get 9x to the 4th. And here we have the derivative of this. We have this monstrosity right here. This is a thing. This is a function. Keep in mind, this is, if you have an x value, you can plug in x's into every one of these x's and get a value. This is a function. It's kind of scary, but I just did it step by step, and I had to explain every step, but usually it won't take as long, obviously, if you just do it by yourself. And yeah, we use the chain rule and the quotient rule. I didn't use the product rule. The product rule is very easy to memorize. If you didn't catch the product rule, you could ask me later, or just look it up in the book or something. So yeah, that's it. Oh, and what time is it? It's 8:11. Yeah, I'll cover the f prime and graphs of f and f prime. So I don't even want to erase this episode 24/7. This is too beautiful. I need. Alright, it's gone. Bye bye. Oh, no, I'll save it. No, I'm kidding. I'm not saving it. No. There we go. Oh, it's gone. Whatever. So what we did on Friday as well is talk about the derivative I'm saying derivative too much. We talked about the graphs of f and f prime. So let's say you have let me look at graphs real quick. There you go, it's matching up. Exactly. So let's say you have a function that looks like this. Kind of like that. This is f. And they tell you, or whatever, for some reason you need to find f prime. They want you to say, they want you to find what is a possible graph of f prime. Remember, what you have to identify which is f prime, or maybe you're supposed to draw it or something. And what to do here is that you have to realize what f prime describes. It describes the slope of f at any given point. We don't care about the y value, or we just care about at the x value, what is the slope. And then we'll graph it. So, you know, this positive above the x-axis means positive slope, and what positive slope is, this is your y-axis, your x-axis, okay, whatever. So, everything above the x-axis, f prime is positive. If f prime is positive, that means, remember what f prime describes? F prime describes slope, so slope is positive. And a positive slope is, you know, like that or that or that. They're all positive slope. So obviously, so f prime, if f prime is negative, that means slope is negative. And I'm not gonna draw any negative slopes. You should know what negative slopes look like. We learned it in pre-algebra. So every time, so x prime becomes x prime. If f prime is negative, then the slope of f at that point is negative. So all you have to do to draw f prime is to identify the slopes of f. So starting at this x value right there, starting at that fx value right here, so see, it corresponds with the x value. This is a positive slope. I'm very tired of this roller coaster analogy I've been doing. So positive slope means you're rising up on the roller coaster. Negative slope means you're having your drop on the roller coaster, right? That's the fun part. A negative slope is when you're dropping. And then a zero slope, which means that f prime would equal 0. So if f prime equals 0, that means slope is 0. And that means a flat slope, right? So you see this is positive slope, positive, positive. But the positive slope is, gang, it's not steep. This is a much steeper positive slope than it is right here. This is, if you draw your tangent line, that's a more positive slope than that positive slope. But they're both still positive. But once you get right here, you end up with a flat slope, and that's your negative slope, or that's your zero slope. And then from then on, you see that there's all negative slopes right here, negative, negative, and then right here, there's another flat slope, another flat one right there, another flat one right there. So usually what you're supposed to do is every time you see that the slope is flat, you should put a dot on f prime at the x-axis, because you know it's going to cross the x-axis, or it's going to go, you know, it's either going to cross it or it's going to go back up. One or the other. So there's a zero slope right there, so it corresponds with right around here. So you know something's gonna happen right there. Same thing with this location right there. You should mark it. There's a zero slope, so you should mark all your zero slopes. This tablet's terrible for drawing circles. I'm using my mouse. So another flat slope right there. Yeah, the mouse is way worse. Never mind. So another flat slope right there, and last one right there. Okay, now we start at the beginning. What do we start with? We start with a rise. The guy is rising up. So that means a positive slope. So f prime has to be positive. But as you can see, this is a much more positive slope than it is right here. So you know that f prime must be decreasing. So there's a positive slope. So let's say this is a positive. This slope right here is a rise of 7, a run of 1. So a slope of 7. So this would be a 7. So if this slope right here is 7, then on f prime at 7 is where it starts, right? Because that's the slope at this point, right? And then by the time it gets right here, let's say the slope is 2. So if this is 2, then f prime at this x value would equal 2. And you see what I'm saying? Like it describes the slope, right? So connect them, whatever. And then you see they're decreasing, and then right when it gets to 0, there's a flat slope. Your guy isn't moving. He's just watching his impending doom as he's going to drop. So, yeah, I hate roller coasters. So he's flat at the very top, slope is 0, you touch the x-axis. Now, starting afterwards, you see this is all negative slope right here, right? If that slope right here is a -3 slope, because this is a negative slope, it's sloping down, right? Then f prime at that point, so tracing down, you know, going down right here. Right here on f prime, it would be -3. The slope would be negative. F prime, if the slope at f right here is equal to -3, then f prime is equal to -3, because f prime literally is describing slope, right? So connect them, and then you know that there's a 0 slope right here, so that somewhere it's got to loop up again, and it would be an inflection point, but we're not going to talk about that right now, obviously. So it would actually, but at the very least, you should know that it should come back up and touch the x-axis, because there's a 0 slope, right? So it comes back up and touches the x-axis. So it goes like that. And then after the 0 slope, you see it's a positive slope again. So f prime is positive. But then it's got to touch the x-axis again, so you know that it's going to curve around again and touch the x-axis. And then after that 0 slope, it's all negative slope again, so f prime is negative. But then you see that there's another 0 slope right there, so somewhere f prime's got to curve back up and touch the x-axis. And then if this was all negative, if this after the 0 slope was all negative, then it would go like this, right? Go like this, right? But after this 0 slope, it's all positive again, so it goes like this. Or maybe not that steeply, maybe like that. So what I'm trying to say here is that it doesn't have to keep, every time f prime crosses the x-axis, it doesn't have to do this. I should have not made an example that does this every time, so it doesn't have to cross the x-axis, then cross it again, then cross it again, then cross it again. It can touch the x-axis and then go back downwards. It doesn't have to cross into positive again. But that's the case if after the 0 slope, it goes back to a negative slope, right? So after a 0 slope, it's negative slope, 0 slope, no, negative slope, 0 slope, negative slope. So f prime is negative, 0, negative. Make that right. So if this is negative slope, 0, positive slope, then f prime's got to be negative, 0, positive. I should have said that on Friday. That actually would make more sense. Hopefully, yes. I'm talking to a computer. I'm going crazy. Oh my gosh, I need to take a break. But we're basically finished. So I'm just gonna finish this. Yeah, so this is drawing f prime using the graph of f. And I'm going to use a program right now. Just hold up. That describes, that graphs, and then I'll show you the f prime thing again. And then I'm finished. How long am I going? It's been an hour. Oh my gosh! If you're still here, then good for you. If you're just skipping around, that's fine too. If you've already gone, then yeah, screw you. I'm kidding. That's fine. I've been going off for an hour, and I'm tired of myself. Okay, this is the last. Alright, so I'm actually opening a software right now. I'm not sure if you can see it. Oh, you can't. Okay, so here it is. This came with. Why am I still using the tablet? This came with my calculator, and it's basically my calculator on a computer. And it's pretty awesome, yeah, because it graphs really smooth curves. So, let's see here. Alright, so let's graph two functions that we, let's go to graph here first, graphs. Let's graph two functions. First function is going to be sine of x, enter. And then we're going to graph now. It's awesome, isn't it? You can also graph 3D graphs, which is amazing in Calculus 3. So graph second function. So what is the derivative of sine of x? That's cosine of x, right? Cosine of x. So what essentially we have here is the graph of f, which is going to be sine of x, which is the blue one, and its derivative, cosine of x, which is the red one, right? And remember what f prime describes? It describes slope. So we can see it describing slope here. Actually, this you may have never noticed it by graphing it back in trig, but this is actually cosine of x actually describes the slope of sine of x. So as you can see right here, as cosine of x is positive, which is a derivative. Remember, this is f prime. Cosine of x is x prime. This is f. This is f prime. So when f prime is positive, or when cosine is positive, the slope of sine of x is positive. You see this graph right here? This when cosine of x, so cosine of x is positive from right here to right here. And then you can see right away that the slope of sine of x right here to right there, it's all positive. When cosine of x or f prime is negative, so when f prime is negative or cosine of x is negative, like from oh, that's not good. No, I don't want to do that. Oh, can even control Z. That's awesome. So when f prime is negative from right there to right there, we see that f, which is sine of x, which is what f prime describes the slope of, is negative. When f prime is negative, slope of f is negative. F itself is not negative, but the slope of f is negative. The slope of sine of, see, slope from here, when cosine of x is negative or 0, like from here to here, the slope of sine of x is negative, even though it's positive right here. Even though the value is positive, the slope is negative when cosine of x is negative. And then finally, when cosine of x is equal to 0. When cosine of x is equal to 0 right there, right there, right there, or right there, we see that f, so when f prime is equal to 0, we see that f has a maximum or a minimum. So basically when slope is equal to 0. Oh, and obviously this isn't always the case like we saw before. There could be an inflection point, which I'll talk about later. But for this case right now, you see that when cosine when cosine of x is equal to 0, when f prime is equal to 0, the slope of f is equal to 0. So there's a flat slope right here. If you visualize a roller coaster guy or whatever, he's at the top or he's at the very, very bottom and begins, and after at the very, very bottom after a drop, and he's getting ready to rise again. So basically, a maximum, a minimum, cosine of x equals 0. Once again, you have a flat slope. Cosine of x is equal to 0 right there. And when f prime is equal to 0, slope is 0. And I am done. If I keep going, I just may faint. So I am done today. That's a total of 1 hour and 5 minutes. Alright, bye.